Okay, so first, let me finish that problem that we didn't get an answer to last time. It was the same situation basically as before, like the information was incomplete. So this is number 5, revisited. And the way it worked, there was 2 kilograms of N2 gas with an initial temperature of 27 degrees Celsius and an initial pressure of 0.1 megapascals. We're given that there was electrical work done at a rate of so this is electrical. And question? This was added to the gas, so this is going to be negative. Negative 0.12 times 10 to the third watts. That's just given. And this whole process takes 10 minutes, so that's 600 seconds. So if you want it as a total change in energy due to this electrical work, you have negative 0.12 times 10 to the third times 600 seconds gives you negative 72 times 10 to the third joules. And you're also given that a total amount of heat over those 10 minutes, heat leaves the system, so Q is also negative, and the total is 12.59 times 10 to the third joules. Okay, so the 600 is 10 minutes. Okay, so we're heading towards Newton's first law. We have the total change in energy due to work, total change in energy due to heat. So the first law says the change in energy is equal to the heat minus the work, and we're trying to find the temperature after 10 minutes and the pressure after 10 minutes. So last time we did we calculated the nitrogen specific gas constant. So R is 8.314 divided by 28 times 10 to the minus third. 28 times 10 to the minus third is kilograms per mole. And we get a value of 296.93. And then the ideal gas law. This is all the same. I'm still just writing down what we did last time. So we have, that's 0.1 megapascals, that's the pressure, times the specific volume is equal to this nitrogen gas constant. times the starting pressure. So this is at state 1. The temperature is 310.15 because it gave it to us as 27 degrees Celsius. And you can use that to calculate the specific volume. So the specific volume is 0.912 meters cubed per kilogram. We have 2 kilograms of gas, so the total volume is 2 times 0.912, so 1.8. I transposed these. 2 times, in both cases, that should be 0.921. So the total volume is 1.842 meters cubed. Okay, and that's going to be important because this is a rigid tank. So whatever that volume is at the start is the volume through the whole problem. Okay, so what can we do with the stuff we have? What we realized we could do last time is that we could figure out the internal energy, or that we could figure out the change in internal energy from the first law. And we know that internal energy for an ideal gas only depends on the temperature. So that seems like it's heading in the right direction. The problem is we don't know the function. We don't have a way to calculate it. Except it turns out that the book has a table in the back for common ideal gases. And so what we were missing was one lookup in a table that we haven't used yet. So let's use the first law. Calculate the change in energy. So change in total internal energy is equal to negative 12.59 times 10 to the third minus negative 72 times 10 to the third. And so the total change in internal energy is positive 59.41 times 10 to the third. So how can we relate this change in internal energy to the temperature? That's what we want. And there's a table. Yeah, I mean, you would have to, right. I mean, you would have to have some kind of function to relate the internal energy to the temperature, and we don't have anything like that. So the table that we have is common ideal gases, or common gases that are treated as ideal gases. And it's all on a per mole basis. So far in the tables, everything's been on a per kilogram basis. But here's what the table looks like. It's all sideways. I'm going the wrong way. Here we go. So ideal gas properties of selected gases. And so there's nitrogen. I'll put this on D2L. But you can see everything's in kilojoules per, well, everything's in whatever per kilomole. So to calculate the internal energy or to relate the internal energy, we're going to have to figure out how many moles of nitrogen we have. But then we have all of it just written as a function of temperature. And if we're unlucky, we have to do a interpolation. If we're lucky, it'll just give us the value that we have. Okay, so it's all per mole, so we're going to have to relate these total changes in energy to internal energy per mole. So we have 2 kilograms, and if you divide that by 28 times 10 to the minus third kilograms per mole, you get 71.42 moles. We know that the change in internal energy is positive 59.41 times 10 to the third joules. So the change in internal energy per mole is equal to 59.41 times 10 to the third divided by 71.42. And you get 831.84 joules per mole. Okay, so tables don't give you change values, they give you state values. And so what we're going to have to do is figure out what the internal energy was at state 1 and then add our change to get the internal energy at state 2. Anybody have any questions yet about where we are in this problem? Okay, so at state 1, the temperature was 310 Kelvin. I threw out the 0.15 because the table happens to have an entry for 310. Yeah. It seemed like overkill. So the pressure is 0.1 MPa. We don't need that. For the ideal gases, you only need one parameter to look things up. And so we're going to look this up in the N2 ideal gas table. And we see that at state 1, the molar internal energy is 6437 joules per mole. Okay, so now the per mole internal energy at state 2 is 6437 plus the change, so plus 831.84. So I'll call that 7269 joules per mole. So now what we're going to do is just scroll down the column of values for nitrogen until we find a per mole internal energy of 7269, and that's going to tell us the temperature. So 7269. So 7270, accordance with my loose attitude towards decimal points and stuff in this problem so far, we're going to say that's good. And so the temperature at state 2 is 350 Kelvin.
You have the same attitude when you're grading tests. No comment.
Yeah. And this table doesn't give pressure. Well, it gives pressure and specific volume, and so use the ideal gas law to calculate the pressure. So pressure times the specific volume of 0.921 is equal to the nitrogen specific gas constant, 296.93 times 350 Kelvin. And so the pressure at state 2 is 112,840 pascals. Any questions? Okay. So now we did the example of the water flowing into the barrel and flowing out of the barrel. Now we're going to do, and so back to conservation of energy. Conservation of mass. We did the one with the liquid water where the density wasn't changing. Now we're going to do one where we have gases and liquids and densities are changing. So this is a heater in a power plant. They say specifically a feed water heater. The feed water is the water that's going into the boiler in order to create the steam that's going to power the turbine or whatever runs the power plant. So the feed water heater is steady state. And it has 2 inlets and 1 exit. And here's what we know. Inlet 1 is water vapor. And at inlet 1, there's a pressure of 7 bar. A temperature of 200 degrees Celsius. and a mass flow rate, M1 dot, of 40 kilograms per second. At the second inlet, we have liquid water and a different set of things that we know. So we know that P2 has the same pressure, 7 bar. The temperature is 40 degrees Celsius. And the cross-sectional area of the inlet is 25 times 10 to the minus 4 meters squared. So this area is the cross-sectional area of the opening. And then at the exit, we have saturated liquid. Pressure at the exit is still the same. Well, it's all the same vessel, so that has to be the case. And the volumetric flow rate is 0.06 meters cubed per second. We want to figure out.
So volumetric flow rate is just rate of change of volume.
Yeah, that's the amount of volume coming in, so or leaving in this case. So I mean, you could measure that if it's pouring into something with you're just measuring how much the volume is changing and whatever it's coming into. This is a liquid, so you can just exit. Yep. So we want to know the mass flow rate at inlet 2, what are m dot 2, m2 dot, m exit dot, and the velocity at inlet 2. And someone made a big deal about this before, so I'm sorry, but this velocity we're going to call, it's really a speed. We know the direction, so we're going to call it capital V. And I'll try to, we're not going to, I don't think there's anywhere in here that we use a true volume, so all the V's in here are going to be speeds. But this we're going to call capital V2. Okay, well, this is a conservation of mass problem, so let's start with the conservation of mass equation. It says that this is in steady state, and so there's no rate of change of mass in the control volume. And so we can just write this as the rate of mass entering is equal to the rate of mass leaving. And so for our problem, that says m1 dot plus m2 dot is equal to m exit dot. I gave an ugly integral expression for the rate of mass flow, but then I said, you would only use that if you're gonna do the fluid dynamics on it. We don't have anything like that. We're basing this all on just averages of motion of material through these openings, and so we're going to use the simple formula that says the area of the, let's see, which one of these, so let's not change what we don't have to. Inlet 1, we know what that mass flow rate is. So I'm not going to change that one. M1 dot. M2 dot, though, we don't know the mass flow rate, so we're going to have to calculate that as the area of that second inlet, the cross-sectional area, times the velocity of the fluid moving in through that opening, divided by the specific volume of the water through that opening. Okay, so this is a speed. This is a specific volume. And when you add those up, those have to be equal to the cross-sectional area of the exit times the speed of water coming out of the exit divided by the specific volume. They are, so if you treat this as a incompressible material, then they would be the same. And normally, so those are both liquids, right? That's normally that, yeah. Right. Well, you could use that as a first approximation. You get a better approximation if you base those specific volumes on temperature. And so just go to any table that has liquid at that temperature, like the saturated water table, and look up the specific volume at that temperature. Okay. But if you used the same specific volume, you'd be in the right ballpark. Okay, so we're given that M1 dot is 40. So 40 plus A2 speed 2 over specific volume 2 is equal to AE times the speed at the exit divided by the specific volume at the exit. And now let's think about what we know about the second inlet and the exit. At inlet 2, we know that area. So I'll replace that. So we have 40 plus 25 times 10 to the minus 4 times the speed at inlet 2 divided by the specific volume at inlet 2. And what do we know at the exit? Yeah, whoops, I went by it. Yeah, so we know the pressure and we know the volumetric flow rate. So in order to use that volumetric flow rate, we need to express that in terms of these other variables that we're dealing with. That's exactly right. Yep. So if you think, I think I drew this picture last time. If you have an opening with a area of A. And you're extruding some that's horrible. I can do better. Okay, so I have to do perspective. That's what screwed me up. See, look how much better that is. Okay, so this is the opening, and it has an area A. This length we'll call L. What's the volume of this red extruded solid? V? Is that what you said? V?
I said 8 times L.
Okay, good. Okay, because yeah, the V thing doesn't really get us anywhere, but it's an okay thing to call it. So A times L. L. And so if we're trying to get the rate of change of volume, that's why I did this thing. Well, that would be equal to A dot times L plus A times L dot, but A doesn't change, right? And so all we're left with is A times L dot. And this L dot, the change in length, is how quickly material is coming through that opening. So this L dot is the speed, V. So we can write this as, and we know that the volumetric flow rate is 0.06 something meters cubed per, yeah, meters cubed per second. So this is 0.06 divided by the specific volume at the exit. That's one equation for 3 variables. So now what can we find from tables? Yeah. So from the saturated liquid water, well, I guess they're all together. From the saturated water table, for liquid water at, what temperatures do we have? At T2, so this at 40 degrees Celsius, that's the temperature at inlet 2. The specific volume is 1.108 times 10 to the minus third. That's meters cubed per kilogram. And for liquid water, that's saturated at 7 bar, volume, this is at the exit, is equal to 1.0078 times 10 to the minus third.
So the fact that it's saturated is just an assumption rather than having anything to do with the.
So yeah, so I was just going to talk about that. So you're talking about at inlet 2, right? We don't. So that water is not saturated. That's liquid water. So why did I use the table for saturated water? For this one, it was appropriate. You know, totally correct. For this one, it wasn't. But I used it because the specific volume is of a liquid is a function only of the temperature. It doesn't change with the pressure. You can't push, you know, at the bottom of the sea, there's a huge amount of pressure, but that doesn't change the density of the water. The only way you change the density of a liquid is with temperature. And so we're just going to use any liquid table where we can find a relationship between specific volume and temperature. And the easiest one to use is saturated, so that's why I used it. Okay.
That makes sense.
Oh.
I was asking the fact that we're saying that it's saturated at the exit. That part is just an assumption and not from the fact that we have water vapor at 200 degrees entering and completely.
That's right. That's something that's given in the problem. They can take the temperature of the water, they know the pressure, and that's something that, you know, these problems are supposed to simulate just taking all the stuff that you can measure and seeing what else you can calculate from that. Okay, so now we can take this stuff, put it back into this equation that says 40 plus 25 times 10 to the minus fourth times the speed at inlet 2 divided by 1.0078 times 10 to the minus third is
No, but the number's wrong. Yeah, it's wrong. V2 should be 1. The specific volume.
this for liquid water at right. Do I have those? I think I might have just given you the numbers wrong. I wrote it wrong here. Here's where I wrote it wrong. So at inlet 2, 1.0078 times 10 to the minus third. At the exit, 1.108 times 10 to the minus third. And so 40 plus this is equal to 0.06. Up here I flip-flopped these. Okay, so 0.06 divided by 1.108 times 10 to the minus third. Now we have one variable, one equation, and so V2 is equal to 5.705 meters per second. So at that inlet, the liquid's coming in at, 12 miles an hour or something. And then the other thing we're asked for is the mass flow rate. So mass flow rate at inlet 2 is equal to 25 times 10 to the minus 4 times 5.705 divided by 1.0078 times 10 to the minus third. Could someone calculate that one? 14.515, and that is kilograms per second. And at the exit, well, we know that that's equal to 40 plus 14.15, so that's 54.15 kilograms per second. Any questions about that one? Yeah, I'll give you that one. That's the only one you'll use for flow rate, for mass flow rate. If it was a long problem like this, I can't imagine I probably would, but yeah, I mean, I guess you should, have in mind that, like, you're in the right table if you can find the right variable from the right input. And if you don't have, if your input is that you want is somewhere in between, then you have to interpolate. But yeah, I think I would probably look it up for a specific value and work from that, so you didn't have to do that. Any other questions about that? All right, so that's conservation of mass. So now we're going on to conservation of energy. So the first law of thermodynamics for control volumes. So previously, when we did conservation of energy, the first law looked like the time rate of change in energy is equal to the rate of energy added through heat minus the rate of energy lost through work. And this is the form if you're looking at a specific amount of material, a specific blob of particles. But now we have to account for some other stuff. Because now we're doing control volumes. So we need to account for energy carried in or out by the new material that's crossing the boundary. So added or removed by the material passing the volume boundary. So we still have all of these terms, but we have to think about, I guess we have to think about two other terms. So here's the time rate of change in energy. And this is in the control volume. And it's equal to the rate of, I'm going to write it as the rate of heat added. It's really, energy added through heat, but minus the rate of work removed. Then plus the rate of energy added, instead of added, let's say this. Let's say carried in at the inlet. The idea is that these particles that are coming in have energy and it's being brought into the system. And then we also have to account for the energy that's being carried out at the exit. So minus the rate of energy carried out at the exit. So now we can write an equation that represents this. The time rate of change in energy in the control volume, that's the EDT for the energy in the control volume. And that's equal to Q dot minus W dot. And now the energy that the material coming in the inlet, what are the ways that material can have energy? What are the three ways that we've talked about that material can have energy? Kinetic, potential, and internal. Exactly. So now we have the mass rate. I'm pulling out the rate of the mass flow times. Now all these are going to be specific properties because we're talking about this. I've pulled the mass out of all of them. So we have the internal energy at the inlet plus the speed squared over 2 at the inlet. So this is speed. Plus gravity times the height at the inlet. So Z is the height. Most of the time, like it's been so far, the kinetic energy term and the potential energy term are going to go away. They're going to be so small compared to everything else that we won't care about it. And then minus m exit dot times all the same stuff. So specific internal energy at the exit plus the speed at the exit squared divided by 2 plus g times the height at the exit. So there's the speed. There's the height. What? That's the gravitational potential energy. So that G is 9.81 meters per second squared. Remember, gravitational potential energy is mgh. So that's what this is. Okay, so now let's think about this work dot. So we're going to expand on that because there is work done on the stuff in the control volume by the stuff pushing in on the inlet, like, hey, stop pushing, you know, it's doing work. And then at the exit, there's work being done on those particles by the stuff in the control volume. Okay, so we have to account for the change in energy due to work right at those boundaries that we didn't have before. Okay, so that's a new thing. So so this is now the change in work inside the control volume plus the work done at the boundary, at the inlet boundary. So I'm going to write that as okay, yeah. So so at the inlet, no, these are both the same, right? So this work is the work done like by the stuff in the control volume on the surroundings. So at the inlet, the stuff coming in is applying a force to the control volume, and so I'm just trying to explain these signs. So the stuff that's going to have positive work. Think about the work done. So at the control volume, at the inlet, the outside stuff that's not part of the control volume is going to be doing positive work on the control volume, right? The force it applies is going to be in the direction of motion of those particles. Okay, with me on that? And at the exit, the stuff in the control volume is going to be applying a force to the surroundings in the same direction as the motion of the particles. So at the exit, you're going to have positive work done by the control volume on the surroundings. At the inlet, you're going to have negative work done by the control volume on the surroundings. And that's why we have here the force at the, so this is the force at the exit times the speed at the exit, and that's positive. And then we subtract force at the, you can think of that as like the normal force that's being, in both cases, there's pushing happening between the outside particles and the inside particles. And that's Fe and Fi. And now we can make one more substitution. These are both speeds. And that's the formula that you've seen for power before. Power is the force dotted with the velocity vector. And so now we can rewrite this as W dot is equal to W dot in the control volume plus that force at the exit is the pressure at the exit times the area at the exit right? That's the force times that speed. And at the inlet, it's the pressure at the inlet times the area, cross-sectional area at the inlet, times the speed at the inlet. So now we can rewrite all this. So we're going to rewrite the first law. And we get dECV dt is equal to Q dot minus the work change in the control volume plus A times okay, I'm going to have to make one more. So we're also going to have to recognize here that this, we've already seen this, is the volumetric flow rate. And we can write that as the rate of mass flow times the specific volume. Okay, so this is a cross-sectional area.
One question.
Yeah.
So we're able to rewrite the force at the inlet and the exit as the pressure times the area, even though it's not like the pressure is putting up against like a solid wall of the inlet.
Yeah, I mean that pressure, yeah, but that's what pressure does. Pressure just pushes on the things around it perpendicular to the boundary, no matter what that boundary is doing. So yes, you can.
It's like an
Yeah, I mean yeah. You don't even have to think of it as a boundary, as imaginary. Well, you know, there's the plane that exactly defines the inlet or the exit. On one side are the particles that we're considering in the control volume. On the other side are the particles that we're not considering. And those two things are pushing on each other with the pressure. Okay, so this is...
yeah, it's a boundary.
Right. Mass flow rate, and this is the specific volume. Okay. So now with that substitution, notice that like this PA speed, I can write as pressure times mass flow rate times volume. Mass flow rate times pressure times specific volume. And so now I'm going to use that and make this substitution. So we have the mass dot at the inlet times UI plus PI with volume I plus speed at I squared over 2 plus G ZI. It's not minus because because we're subtracting this work from this. So in the version of the first law up above, we're subtracting the work dot, and so we're subtracting a negative inlet term and subtracting a positive exit term, and then minus E dot times UE plus PE specific volume E plus V squared over 2 plus G ZE. Okay, so why did I show you all this? I mean, it's a derivation, but, you know, like there's some use for derivations, yeah. That's specific volume. Yep. That's speed, yep. Okay, so I showed you this because we're gonna shorten one thing. Look at what happened here. So this is, I was saying before that this enthalpy thing, you know, it sort of has an interpretation, but mostly it's just a mathematical sort of, it's a set of terms that show up together a lot. And here's the first time we've seen it show up. So we went through all this, thinking about the stuff that we know and understand, and we just came up with this term in two different places that we can rewrite as the specific enthalpy. So the final form is d dt is equal to q dot minus the work done by the control volume dot plus mass at the inlet dot times the quantity enthalpy at the inlet plus the speed at the inlet squared over 2 plus g z at the inlet, and then minus the mass flow rate at the exit times the quantity specific enthalpy at the exit plus the speed at the exit squared over 2 plus g z at the exit. Okay, so this is the first law for a control volume. And like you noticed, it's pretty ugly. But there are going to be simplifying assumptions pretty often. So next I want to talk about what are some of the common simplifying assumptions. Does anyone have any questions about that? I mean, you know, like the take-home message here, I mean, I think derivations are useful if they're simple enough take-home messages that you could recreate it in some way or use it to remember something. Like that's why derivations are useful. This is probably too I'm not, without having notes in front of me, I'm not sure I could trace the steps back on that. Maybe I could, but I don't think there's really any reason for you to get to the point where you can trace that back. But the key thing is that we started that derivation with the first law that we know, and just by reasoning out what's happening at the inlet and the exit, we came up with this enthalpy term. Okay, that's what I wanted to show. Okay. Yes, well, it depends. You know, I guess it depends what you know before you have to solve it. It's an ODE if you're solving for the energy in the control volume, or Q or W, and you know all the other stuff. It's a algebraic equation if you can start knowing what those derivatives are. So it can be a differential equation, but not necessarily. No, this is an ordinary. Anything that has to do with total derivatives. And so that's right. The difference between ordinary and partial is how many independent variables there are, not how many dependent variables there are. All right, so this is ugly, but it will often simplify. So often one or more of the change or the rate of work done by the control volume, or the rate of energy added through heat to the control volume, or the kinetic energy, or the potential energy, 0. And so here's why. So first, let's think about when Q, the heat added to the material in the control volume, dot is equal to 0. If it's well insulated, the control volume, or if the surface area is small, so the surface area of the control volume is small, you know, even if it's copper or something, if the surface area isn't big enough to allow the stuff inside and the stuff outside to exchange heat, then there won't be any change in the control volume. Small temperature difference between the control volume and the surroundings. And 4, if the material moves fast through the control volume, then there just isn't time for heat exchange to happen. If you have a closed system, then whatever process is taking place, all of those molecules are captive there. So the thing can happen fast or whatever, but over that whole process, those things are there for And so in this, we're talking about particles that often all of the particles are starting here and ending here in the process, you know, during the process. Sorry. Okay, so when is there are no energy added or energy done by the control volume. Yeah. Okay, well, first, if there's no displacement at any of the boundaries, like in a tank or any kind of rigid thing, no displacement of the control volume boundaries, then W dot is 0. Well, you know, actually, these are a little, okay. No rotating shafts. Yeah, that's right. And 3, no electric work. Okay, so the work done by the control volume is 0 if all of these hold. Okay, so if the boundary is rigid and there's no motor running a rotating shaft and there's no electric work done, then W dot is 0. And I just want to make a distinction between that and this one up here, where Q dot is 0 if any of these hold. And then the last one, kinetic energy and potential energy. These are usually small compared to the other changes in energy. So we're usually going to ignore these. And so the next thing we're going to do is finally we're going to get to using this equation on some processes. We're going to do it for material passing through nozzles and diffusers. And you can think of those two things as the same thing, just the materials going in the opposite direction. So a nozzle is like, you know, a hose nozzle that you use to spray the water farther. If this is 0.1 and this is 0.2, the material is going through this way. So this is a nozzle, and in a nozzle, the speed is higher at location 2 than location 1. And the pressure is the reverse of that. So the pressure is higher at location 1 than location 2. So a nozzle is like when you put your thumb over the hose, you make the exit smaller than the inlet, and you increase the speed coming out. And a diffuser. This is 1, this is 2. The material's flowing this way. And just everything is reversed. V1 is greater than V2, and P2 is greater than P1. So, yeah, this is speed. Increasing the speed decreases the pressure, so those are always reversed. And if you remember that the pressure is always opposite the speed, then it's easy to remember where the speed is higher or lower on these two. Okay, so we'll do that next time. That's it.